thermocouple device, a thermometer, thermistor, an infrared camera, and a spot radiometer or IR thermometer gun. These measurement technologies and what they truly measure, for example, a thermistor measures changes in resistance associated with changes in temperature. A thermometer measures changes in volume associated with changes in temperature. A thermocouple, it measures changes in voltage associated with changes in temperature. IR thermometers also measure changes in voltage associated with changes in temperature. And an infrared camera, more specifically the IR camera we will discuss in today's webinar, it actually measures changes in resistance associated with changes in temperature. All of these instruments that I've mentioned and listed here report a temperature value based upon the measurement of some other parameter. Now, for today's discussion, we will focus on IR thermometers and IR cameras. We're going to review a little infrared theory. So let's start at the molecular level. For example, as a medium, whether it's a fluid, gas, or solid, heats above absolute zero, molecules within that medium start to move about. As these molecules move around, they collide with each other, creating energy release in the form of photons. As the temperature of the medium increases, so does the molecular movement and the resulting collisions. Thus, an increase in temperature produces an increase in the release of photons. This form of heat transfer that is caused by the release of photons is known as thermal radiation or infrared radiation. Thermal or infrared radiation is what is sensed or seen by an IR thermometer and IR camera. The chart shown here on slide 5 is a representation of the electromagnetic spectrum. From the chart, we see how infrared radiation relates to other forms of electromagnetic radiation. Some key takeaway points are infrared radiation wavelengths are larger in size than the visible wavelengths our eyes are tuned to see, yet they are shorter than radio wavelengths. Like visible light, infrared radiation travels through space at the speed of light. Like visible light, it can be focused, it can be reflected, it can also be refracted. An important property in the field of infrared theory is emissivity. In basic terms, emissivity describes how well a target or material emits infrared radiation. A perfect emitter is known as a black body and has an emissivity value of 1. But in reality, there are no perfect black bodies, so most materials have an emissivity value less than 1. Let's take a closer look at the property of emissivity on slide number 7, and how this emissivity might affect measurements taken with an IR thermometer or infrared camera. In this example, we want to sample and report the temperature of a perfect black body. Thus, the emissivity of our target is 1. Or, in other words, the infrared radiation from the target is 100% emitted from the target surface. This is a good time to point out the difference between actual temperature and apparent temperature that I have labeled here on the slide. The actual temperature is the actual or true temperature of the target of interest. The apparent temperature is the temperature value reported by our IR thermometer or IR camera. I say reported temperature value and not measured value because, as you remember, our IR thermometer and IR camera do not measure temperature. They measure the effective temperature, perform some mathematic calculations related to a calibration procedure, and then report a temperature value. Our goal in using IR thermometers and IR cameras is to try and make our IR instrument reported apparent temperature be as close as possible to the actual temperature. Now, in reality, the objects we are likely to measure are not perfect radiators or black bodies. Our targets have emissivity values less than 1. As such, the total radiation that reaches our IR thermometer and IR camera could be a combination of emitted, transmitted, and reflected radiation. Now, transmitted radiation is that radiation which passes through the target of interest. This is much like seeing light pass through glass. Reflected radiation is radiation from a surface or a source in front of the target of interest that reflects off the target of interest. This is like seeing your image reflected in a mirror. The temperature that is associated with this reflected temperature is known as reflected apparent temperature, and sometimes it's known as T reflected or T background as well. Now, an IR thermometer and IR camera sees the total radiation from the surface of the target, and neither the IR thermometer or IR camera can differentiate between the various sources of radiation on their own. It is the end user who must tell the instrument what makes up the total radiation seen by the instrument. This way, the instrument can calculate and report an apparent temperature close to the actual temperature. Now, as a side note, I will point out that by the end of this webinar, you will learn that IR thermometers have an inherent deficiency that actually limits their ability to accurately calculate the temperature of targets that have an emissivity value less than 1. Okay, now that we have reviewed some infrared theory, let's discuss how IR thermometers and IR cameras see infrared radiation and report a temperature value. First of all, let's review the basic operation of an IR thermometer, sometimes called a spot pyrometer, IR pyrometer, spot temp gun, or IR gun. They're all one and the same. The IR thermometer has within it a single detector element that senses infrared radiation. This detector is typically a thermopile. A thermopile is an electronic device that converts thermal energy or thermal radiation into electrical energy. Thermopiles do not respond to absolute temperature, but they generate output voltages proportional to a local temperature difference. Now, this changing output voltage from the thermopile is measured and calibrated to a corresponding temperature value, and the resulting temperature value is then reported on an LCD display. A key parameter for all infrared thermometers is what is called the distance to spot ratio. This DS ratio defines the area measured by the device at a given distance. The IR thermometer measurement area is illustrated in this slide by the red circles, which increase in size as the target distance increases. The temperature reported by the IR thermometer is not the result of a single point measurement, but of an area. In this example, all the IR radiation from the red highlighted area is being sampled, averaged, and used in the calibration calculations. It should be noted that the red laser that is available on most IR thermometers does not measure temperature. It is a separate beam that simply serves as a pointing device. Now, keep in mind the red laser can shoot a very long distance. However, the infrared sensor in my IR thermometer only samples effectively at short to medium distances. And this again depends upon the instrument's distance to spot ratio. Now let's look at the operation of an infrared camera. In this example, we are referencing a FLIR T420 camera. This camera has an uncooled microbolometer focal plane array infrared detector. A microbolometer is a thermal-based sensor, meaning it produces a resistance change when heated. The focal plane array in our camera is made up of 320 by 240 or 76,800 detector elements, each one of these elements being a single bolometer. With the lens of our camera, we can focus infrared radiation from the target onto these detector elements. As the radiation strikes the elements, they heat up and their respective resistance changes. Using a readout integrated circuit, we can measure the resistance change for each element and convert the reading to a digital count. Most IR cameras digitize at 14 bits, or 2 to the 14th power. The digitized data for each element is then calibrated to a temperature, assigned a color or grayscale value, and presented as an image. Now, because our image from our infrared camera is made up of individual detector element measurements, we can use analysis tools to highlight specific elements and display their respective values. I can use an area tool to display the maximum, minimum, or average temperature within an area. I can use spot tools to display the temperature values from any element within my infrared image. In a way, my T420 camera is like having 76,800 IR thermometers in the palm of my hand available to make temperature measurements. Okay, now we're going to dive in and conduct an experiment. And the purpose of this experiment is to illustrate the different performance between these infrared sensing technologies. Now, the experiment that I've set up for today is a very simple one. I will place multiple pieces of black electrical tape that has a known emissivity value onto a shiny stainless steel cup. My target sizes, based upon the tape, will include 50 millimeter, 20 millimeter, 10 millimeter, 5 millimeter, and 2.5 millimeter square targets. I will fix a thermocouple inside the cup and fill the cup with hot water. Now, from our previous webinar titled Thermocouple Measurements versus IR Camera Measurements, we learned from that webinar that bead wire thermocouples do a good job of reporting temperatures of gases and fluids. As such, the thermocouple will be a good indicator of what my cup internal temperature is and a very close indicator of what my cup surface target temperature should be. So it's a good baseline for me to compare these other measurement devices against. So I'm going to do that. I'm going to take multiple measurements of my electrical tape targets that have a known emissivity value with the IR thermometer and IR camera, and I'm going to compare the results. So in the experiment, I'm using the following equipment. I'm using, again, the T420 FLIR infrared camera. I'm using an X-Tech Type K thermocouple. I'm using 3 different IR thermometers, and I'm not listing the manufacturers or model numbers to protect the innocent in this webinar. But I will list the individual specifications on the following slide. And as I mentioned previously, I am using Scotch electrical tape because it has a known emissivity of 0.95. It's a great emitter. And so my targets, again, are made up of that electrical tape. In slide 16, I have a chart that displays or compares the key specifications for our IR measurement instruments. And from the chart, we see our instruments have certain specifications in common. For example, all of our instruments, first of all, they see infrared radiation, and they happen to sense that radiation in the long wave spectral band. They all have similar specified accuracy specifications. They all have adjustable emissivity settings. There are some specifications that differ, though. They all have different field of view characteristics, meaning some are better at making close-up measurements than others, some are better at making distance measurements than others. And only the IR camera has an input for reflected temperature, humidity, distance to target, and external optics transmission. So I have additional object parameters that I can adjust or set on the infrared camera. Now, our experiment will demonstrate how these differences in these specifications impact our measurement results. Okay, so let's look at the first measurement results. And these results were taken with our very first IR thermometer, and I'm going to refer to this as IR Temp A. This chart shows the difference in reported temperature values from my IR Temp A, my temp gun or IR thermometer, and the internal thermocouple. We see that our first IR thermometer reports a fairly constant 2-degree difference for the 50 millimeter and 20 millimeter targets. However, the measurement error grows significantly for the 10, 5, and 2.5 millimeter targets, topping out at more than 14 degrees error for our 2.5 millimeter target. Now let's add the measurement results of our second IR thermometer, or what I've been calling IR Temp B, and we'll apply this to the same chart. We see almost the exact measurement pattern for IR Temp B, with slightly less error than our first IR thermometer. Now let's add the measurement results from our third IR thermometer, and I've been calling this IR temp C. This IR thermometer shows much less measurement error with an initial difference of approximately 1 degree from the thermocouple reading on the 50 millimeter target. However, we still see significant measurement error on the 2.5 millimeter target with an error difference of 11 degrees C. And finally, let's add the measurement results from our T420 IR camera. As shown here, the IR camera had very good measurement results, maintaining less than a 1 degree difference from the thermocouple reading for all the sample targets, including the 2.5 millimeter target. So why the difference in measurement results for our IR instruments? Why are we seeing such a difference between these? Well, let's dig into that now. On slide 21, I will address the main cause for measurement errors in our experiment. As you may recall, every IR thermometer has a distance to spot ratio, and knowing the DS ratio and the target distance, we can calculate the spot size. The spot size is the area sampled by the IR thermometer at a given distance. For example, if our IR thermometer has a DS ratio of 30:1 and the distance to target is 30 inches, the spot size will be 1 inch. If the distance to target is 60 inches, the spot size will be 2 inches. A very important point is to accurately sample a target and produce a valid temperature output, the target must be smaller than the spot size. On the next slide, I show here the various distance to spot ratios and minimum spot sizes for the IR thermometers used in our experiment. The smallest sample areas we can capture with IR temp guns A and B is 12.5 millimeters. IR temp C is a unique IR thermometer. It actually has what is called a close focus capability. And this capability allows this particular IR temp gun to measure a minimum spot size of 6 millimeters. So how do distance to spot ratios and spot sizes relate to an IR camera? Like the IR thermometer, our IR camera has a spot size. The spot size represents what an individual pixel element will sample. The spot size will change based upon the camera lens combination and the distance to target. For our experiment, I used a 25-degree lens with our T420 camera. And based upon this camera lens combination and a distance to the target of 0.2 meters, our minimum spot size was 0.6 by 0.6 millimeters. This slide here shows a zoomed-in view of our 2.5 millimeter target. This is my tape target as it appears in infrared. And as you can see, at a distance of 0.2 meters, our camera lens combination results in about 64 camera detector elements sampling our target. I have more than enough pixels available to sample my target and make a measurement with the infrared camera. Now, as a side note, as a general rule, when using an IR camera to sample targets, it is recommended to use a camera-to-lens combination that will maintain a distance to the target that will allow a 3 by 3 pixel sampling. Now, why is this? Well, this ensures we will capture at least 1 pixel squarely on our target. And if we have at least 1 pixel, we can measure it accurately. Now, let's go back to our results that I have displayed here on the chart. And what I've done is I've superimposed the minimum spot sizes of our temp guns from our experiment. From the chart, we see the temp gun measurements. The error increases dramatically when the target size is smaller than the minimum spot size. From the chart, though, we also see a slight variance in measurements from the thermocouple before the minimum spot size. What might be causing this difference in apparent temperature from the target actual temperature before our target size is smaller than the spot size? Okay, this slide here is a graphical representation of our experiment, with the block on the right representing our stainless steel cup. Now, because our cup is opaque, the total radiation from our stainless cup is a combination of emitted and reflected radiation. Now, from the lookup tables, from emissivity lookup tables that are available, I determined that my stainless steel cup, it has an emissivity of 0.075. What that means, from the perspective of my IR thermometer and IR camera, what that means is that 7.5% of the radiation sampled is emitted from the cup, while 92.5% is reflected radiation. Stainless steel with this low of an emissivity value is extremely difficult to measure, if not impossible. So to improve the emission characteristics of my stainless steel cup, I used the Scotch electrical tape, which I stated earlier has an emissivity value of 0.95. Now, from my IR thermometer and IR camera perspective, 95% of the radiation sampled is emitted from the cup, while only 5% is reflected when I'm looking at the Scotch electrical tape. Now, because my goal is to make my instrument apparent temperature equal my actual temperature, I must tell these instruments, my IR thermometer and IR camera, how to differentiate between these two contributing sources of radiation. I do this by adjusting the emissivity setting on my instruments. And you may remember from the comparative chart, all of my instruments had an adjustable emissivity setting. I have to tell my instruments that I know that 5% of the radiation is reflected. But of that 5% reflection, how much is that radiation? How much does that radiation influence my measurement? If the reflection from a hot or cold source, if that reflection is from a source that is hotter or colder than my target of interest, how might that impact my measurement? I believe the following slides will help illustrate the influence that T reflection or reflected radiation can have on IR measurement. For example, let's say that my target of interest has an actual temperature of 50 degrees C. And let's say I have a source that is being reflected off of my surface that is colder than 50 degrees C. In this example, I have a cup of ice water. If the source of T reflection is a cold source and I make no adjustments to my camera or my thermometer, will my apparent temperature measure higher or lower than the actual temperature? Again, if I make no adjustment to my thermometer and my camera, how might that cold reflection impact my reading? It will read less than what reality is. Let's look at the same scenario, but now with a hot source contributing to T reflected. Remember again, I've made no adjustments to the emissivity setting of our IR instruments at this point. Will my apparent temperature measure higher or lower than the actual temperature? It will measure higher. The critical point to be made here is that to accurately sample and report a temperature measurement, I not only need to tell my IR instruments the emissivity of my target, but I must also tell my instruments the temperature that is being reflected as part of the total radiation. Herein lies the challenges with infrared thermometers. The infrared thermometers I used in my experiment had no input value for T reflection. This creates an inherent difficulty in using an IR thermometer when making measurements on targets that are not perfect black bodies, or making measurements on targets that have emissivity values less than 1. There is no way for me to compensate or adjust for the temperature of that reflected radiation. As I mentioned, as part of this webinar today, I'm going to explain to you how the usage of IR cameras eliminates or overcomes the guesswork associated with using IR thermometers. And that's what we're going to talk about now. And I'm going to highlight this capability through another experiment. In the exercise, in this experiment, we will examine a printed circuit board. I've displayed the printed circuit board here visibly, and our objectives are listed as follows. This is what we're going to do in our experiment. First, we're going to determine the maximum temperature and location of that maximum temperature on our printed circuit board. Second, we're going to determine the temperature of the IC, the small IC that I've highlighted here. And then finally, we're going to determine the temperature profile of the highlighted chip. Okay, let's go. So first of all, here are the results using my infrared thermometer to determine the printed circuit board maximum temperature. And the process here was very basic. I simply scanned up and down and back and forth across the target, and I paid particular attention to the LCD display of the IR thermometer. And when I saw what I perceived to be the highest or hottest temperature, I zeroed in on that location. And I did that with all three of my infrared thermometers, and the area here highlighted in red is the approximate location of my maximum temperature reading. Now let's compare our IR thermometer max temperature results to those utilizing the FLIR T420 camera. The T420 thermal image and corresponding color temperature scale clearly show the thermal variations on the printed circuit board. Those areas in my thermal image that are white represent the hottest temperatures on the printed circuit board. And a feature with the thermal analysis software that is included with the T420 in the thermal benchtop kit, that software allows the end user to pinpoint the maximum temperature on the image, or pinpoint the maximum temperature in a region of interest. And that red arrow point that is shown here on the image is highlighting the location of the max temperature of the printed circuit board. And the analysis results displayed here on the right show the corresponding temperature values. And the maximum temperature at that spot location is 48.7 degrees C. It took less than a second to indicate or find that location and display that temperature value with my T420. Now let's go to our next task. Task number 2, which is to measure the temperature of a specific IC, and I've highlighted that here. And the sampling process for this was simple as well. I basically hovered over the target of interest, which was the IC, and I read the value off the IR thermometer, and I've listed those values here. Now we can compare this to the results of the thermal camera, the T420 camera.
Hey Dave, can I interrupt you for a second?
Absolutely.
We had a question. How come the emissivity was 0.95 for the integrated circuit?
You know, I left it at 0.95 because that's what I was measuring with the tape, and basically I left it where it was previously. And also just doing a very basic check of the IC and looking at its reflective properties in the visible spectrum, I determined, yeah, it's probably around the same, so I left it at 0.95.
Thank you.
Thank you. Okay, so what this shows here is the differences in temperature from my infrared thermometer and my infrared camera. And one point to make from the thermal image is not only do I have a single temperature value from the IC, well, actually I don't. I have a distribution of temperatures. I actually have a thermal profile across that IC, which becomes visible when you look at it with the infrared camera. It was impossible for me to see this with the IR thermometer because, again, of that distance to spot ratio. I was averaging everything in that area. So I missed the fact that there is actually a thermal profile or varying temperatures across that IC. Okay, now my last task. The task here was to show a thermal profile of the designated chip. And what I have displayed here are 3 value tables, each one representing the results from a different IR temp gun. And I apologize, the one labeled on the bottom there should be IR temp C. So A, B, and C in descending order. And I can look at these and I can see the numeric values associated with me hovering over different locations on the chip. And the reading in the upper left-hand portion of the table represents the reading in the upper left-hand corner of the chip. The center cell in my tables represent a center measurement off the chip. Now let's look at the same profile using my T420 camera. And as the saying goes, a picture is worth 1,000 words. And again, because each pixel in my thermal image represents a temperature value, I can actually extract the numbers behind this image and present the data in different ways. And that's exactly what I've done here in slide 39. This is a three-dimensional surface plot of our chip. Essentially what I did is I exported the data points utilizing the analysis software that comes with the Benchtop test kit, and I imported those data points into Microsoft Excel. The different elevations and color variations here represent the varying temperature differences across our chip. And I'll close by asking this question: how is that for eliminating guesswork? In conclusion, let's review the results. What did we learn from this experiment? First, let's talk a little bit about the IR thermometers, the advantages and disadvantages associated with utilizing this technology. First of all, the advantages, where, well, IR thermometers are relatively inexpensive when compared to IR cameras. Additionally, they are a non-contact method for reporting temperature. On the disadvantage side, though, IR thermometers have limited spot size, which means they are not accurate at sampling small targets. It is also very difficult, if not impossible, to align the IR thermometer perfectly over small targets that I'm interested in measuring. So there is a certain level of guesswork involved when trying to find targets with a spot pyrometer or IR thermometer. Another disadvantage is the need to know the correct emissivity value for the target of interest. I need to know that in order to make the measurement. However, this limitation is overshadowed by the inability to enter any reflected temperature information. That is a critical parameter in making the mathematical calibrations to present a temperature value. Now, the single point measurement also contributes to the difficulty to accurately or pinpoint the target of interest. This increases the time it takes to sample targets. For example, when I was sampling the chip and trying to gather temperature information from each of the corners, it took me a very long time to do that. And then finally, the close-up measurement option is not inexpensive. My IR Temp C was a fairly expensive instrument, costing roughly around $1,000. And entry-level cameras are available today costing around $1,200. All right, now let's review the advantages and disadvantages for our IR camera based upon our findings. First of all, the advantages are the temperature reporting is pretty accurate, as we saw from our results, across multiple target sizes with multiple emissivities. And the camera captures information with no target contact, which again is another advantage. And it does this for several thousand spots, not just a single spot, which is another advantage. The camera produces a thermal image, which is very easy to interpret, but there's also quantitative data behind that image. And that allows for quick and easy analysis either on the camera or in analysis software, or actually exporting the data and analyzing it in third-party softwares. Included with the Benchtop test kit is a recording and analysis software that makes the T420 a great instrument for capturing snapshots and thermal movies. And finally, the T420 camera not only has the ability to adjust emissivity, but also the reflected temperature, which is critical in reporting accurate temperature readings. If our goal or objective is to have our apparent temperature be as close to or equal the actual temperature or true temperature of our target, we really need to adjust both of those parameters. So what are some of the advantages or disadvantages? Well, again, IR cameras are typically more expensive than IR thermometers, but we're seeing that change. They're becoming closer in price point. So this disadvantage will be going away. And then also the final disadvantage is that we do need to know the emissivity value of our targets of interest in order to accurately report temperature measurements. And if you've happened to look at the Technitool webinar schedule, you'll notice that the next webinar on the schedule is specific to addressing the property of emissivity and how to deal with it when utilizing infrared technology. So you may want to look out for that invitation as it comes across your email and participate in that, as we will be addressing that more specifically. Now, that's really the end of the webinar for today, but I thought, since I've been referring to these benchtop test kits throughout the webinar, I would let you know what they are. And essentially they are an infrared camera, a couple lenses, and software that allows you to take essentially a turnkey kit out of the box and start sampling and making measurements and reporting temperature values, much like I've shown you here today. This is the T420 thermal benchtop test kit, and it highlights what it includes. And I will point out that that 45-degree lens that's included with this particular kit allows you to resolve down to 120 micron spot size, which is amazing. You can get very close and resolve very small targets with this particular kit. And there's a second kit available, the E40 benchtop test kit. This camera has a lesser resolution. However, it's still very powerful. It does come with a 45-degree lens as well that allows you to do close-up work to 200 micron spot size, includes real-time plotting and recording software, and will accomplish the task that I illustrated here today in our experiment. I want to thank you again for taking time out of your schedules to meet. I've listed here the contact information for have questions about this technology, the webinar, benchtop test kits. Please give them a call, visit their website here. I've also listed my email address, and I did that because if you have some specific application questions regarding the usage of infrared thermometers or an IR camera, please feel free to send me an email, and perhaps we can connect and we could even discuss in more detail your specific application.